Welcome to class 7.
Did you take down the other video that was on YouTube?
No?
Okay. Is it unlisted?
Yes.
Okay. Wait, what YouTube video?
The one that I sent to the list?
So we can't try to make it go viral?
No.
You recorded it.
Did I? We'll send it out. It's in an email. It's on the list.
It's on the list. Anyways, so hopefully the video helped. Did the video help from last time? All right, perfect. So obviously it's now a reproducible process. We can continue to videotape this whole situation. Okay, so as usual, let's go through the homework 6 status, I guess. It's not a retrospective yet since we're just going to extend it for this next week. So typical status report on the class. It's in general. We're currently at 73 graded students plus 1 auditing. So I think we've now passed the 50% drop rate. And I expect to see probably another 10 or so at least withdraw.
So I have a question. Does the faculty say anything to you about so many people dropping?
I'm sure that it could come up after the semester. I don't know.
But they don't get to do surveys, so.
Huh?
But they don't get to do surveys.
That's true. That's true. Yeah. So at the end of the semester, there'll be a course evaluation, right? And then that, of course, will get reviewed, and that will determine if they want me to teach this course again or not.
The disclaimer was the first slide.
Huh?
Drop now.
Yes. Exactly.
Put it on there.
Yeah.
I mean, I will say this is like the class I probably learned anything in the last 4 years. So
Perfect. That's good to hear. Yeah, so we're definitely trying to strike a balance between a class that forces you to learn and a class that doesn't kill people.
well, you're almost killing us.
Yeah.
I'm gonna tell you this right now. We're 40 hours a week
nudging
of
towards
homework.
learning
It's
side.
definitely killing a lot of us.
Yeah.
I'm thinking you meant to strike a balance between the class that people learn in and the class that does kill people, right? Perfect balance.
Exactly. Yeah. Yeah. So, anyways, of course, hopefully it hasn't been so brutal, especially with makeup homeworks and so forth. But we'll continue correcting. So, right now, as usual, we have the curve just boosting people all the way to the top, which is not that great. And I again haven't had a chance to do the figuring out it without the curve or an alternate grading system to boost people that really just get screwed by being right below the threshold. And right now we only have 38 people that have anything more than the example shellcode that we went through in class.
What do you mean when you say have more than?
Have more points than could just be solved by using that exact shellcode that we created. So that shellcode can get you 16 points. And a large part of the class right now, so there's 38 people that have something like 40, 60 or more points, and then a lot that have just 16, a couple that have 0. So there are a couple of things that let me see if I have these slides. All right, there are a couple of things that people have difficulties with. One of them is redirecting control flow in general. There's one challenge that requires you to actually specify the address to jump to. And this seems to be a tricky thing, even though all of homework 4 was like this. So does anyone need us to kind of walk through that real quick?
Yeah.
All right.
Are you sure it's not because of the buffering issue that people are having trouble with it? I would like an
Is there a
explanation
buffering
for
issue?
Because I feel like I'm having buffering issues too.
So
What did experience is?
it depends on how you interact with this thing, right? So the correct way to interact with almost all of these things is to use tools created by hackers. So specifically something like Pwn tools. So who's using Pwn tools to interact with this stuff? And who's using Pwn tools and having trouble? All right, so let's look at this. Ah. So, if we have something like, what is the level with, it's 3, right? All right. So if you just run Baby Shell 3 teaching, do you see this when you run? Okay. When you run it, it says reading OX 1000 bytes from SCDN into the address, right? Then I type something, and then says it does not directly execute your shellcode. You'll need to force it to do so by overflowing and overriding the return address from the function, right? This makes sense. This is very similar to what you did in homeworks 4 and homeworks 5, right? For the baby Pwn binaries and then for the homework 4 binaries. So, if you overflow the shellcode buffer and override the return address of the vulnerable function, and it returns to an address you control, what should that address be? That exact address that's given right there. That's where your shellcode is being read into, and that's where you need to redirect control flow to make that happen. So who that was having issues did not have this address printed out to them? All right, so that's the trick to level 3. You have to see the address. And this is in some sense an information leak. It says, hey, this is where, in this case, your shellcode will be loaded. And then you simply override the return address to point there, and you're done. We can run it again, and you see that it's a different address, right? So if you run it twice, here's E0, here's B90. Different address every time you run because of address space layout randomization. Overflow it with this address that's provided, and you got it. The teaching, or the testing and the teaching one, in this case, both leak the address. I don't know why this leaks it twice, actually. That must be a messed up if statement, but the point is you have this address here. Now, it is not impossible that there's some weird buffering stuff that happens and your address doesn't, and you don't see this. But let's just try this out in Pwn tools. So we launch the process. Let's say blah equals r dot read until this thing that it says here from stdn into. So here's everything right up until it's about to print the address. And here's the rest. Here's the address. So that we're printing is the address. We can, of course, convert this into an integer. This will error out because I'm also including the dot and the space. It's just showing you it errors out because it's trying to do the address dot on a new line. And instead, we just say strip out spaces or new lines. Sorry. And dots. And that is the, why is this not the same as what it was printing before? Exactly, because it's not hex anymore. So of course, let's say adder equals this. And if you do hex adder, boom, leaked address, that. Let's take away this print here. It's unnecessary. Boom. This is a very typical flow during exploitation. You connect, you do something to trigger a leak of the address of some information. In this case, it is a stack address. And from there, you just use it in the exploit that you crack. Okay, so aside from any sort of buffering, anything, that works.
So the issue that I was having was with the return of the flag.
Right. So then there's the return of the flag, which is kind of independent of this issue. So now, let's say we have this situation. So now we send our shellcode, overflow the return address. So let's say shellcode. Where's our shellcode here? I actually prepared a bunch of shellcode in this directory. Here's our shellcode. We read it. So it reads OX1000 bytes. It only reads OX1000 or it reads more? Let's figure that out.
Oh no, you have to go to, doesn't matter, you just have to go to F28.
No, I understand, but where do we start overflowing at?
F28.
If you send the F28 bytes, that's your.
Oh, okay. Awesome.
Have it on the stack.
Oh, yeah, see, very important to look at all of the data that the program gives you. So it says OF28 bytes between the start of your shellcode and the stored address. So we grab the shellcode, we left justify it to OXF28. That means pad the shellcode to the with things to the right so that the shellcode is all the way to the left, but the string is OXF28 bytes long. And then we add the address. And let's add a bunch of it. Let's add 10 versions of the address, or 10 concatenated addresses, just in case there's some other stuff that we're not accounting for there. So this will eventually overflow the return address and return into our shellcode. Whoops. Then we want to read everything that the program gives us. And the program did not crash.
Oh, you're not sending. You gotta send it.
And we got to send it. That's very smart. Okay, so print r.readAll, and there it is. Cool. So of course the program gets the shellcode, disassembles it, and then prints. Now, it's possible that if
I think it's because I was catting it in.
if you're catting it in and weird buffering stuff happens, it might not print out right away. You might write to the socket, but it might not pop up on your shell.
Is there a section in the Pwn tools documentation that explicitly talks about this kind of stuff? Because I did not know that was possible.
Which specific part?
How you could how you just pad it to
So that's Python.
Python just in general?
Yeah, any string. Left justify 128. And here you can see all these spaces in here, right?
Oh, okay.
You can also say left justify it with the number 0 and so on. So that's Python. What else? What other tricks did we use? Dot strip is also Python. Any string you can strip out. So if we have this string right here, and we will say actually strip out all zeros from the end, strips them out. You can say zeros and f's, strips them out,
I was using instructions.
Yeah, Pwn Tools provides a functionality to send 32-bit, 16-bit, 32-bit, and 64-bit integers as bytes according to the architecture correctly. So P16 is a 16-bit little endian integer in this case. So if we do OX0102, we see it gives us OX0201. Why is it backwards? Exactly. P32, 32 bits. P64, 64 bits. And this P64 was what we were appending. We appended 10 copies of our address. That was just being lazy. Since we know exactly OXF28 is the distance to our shellcode, or to the return address, this should also work. And it does.
So something important with the buffering, your shellcode almost certainly has an exit call at the end, so exit 0.
I believe my
Make
shellcode.
sure all of the buffering gets finished at the end. Whereas if you don't have an exit call, it can crash and not send out the standard out.
That is true. I don't think mine does, but I agree with you in general. Yeah, I'm not calling exit.
Okay, but that can be an issue.
That can be an issue. So if you're having trouble with buffering, make sure your shellcode exits cleanly, or your shellcode can also call a system call to flush the buffer. What is that system call? Let's find out.
Didn't you disable buffer?
I think I might have forgotten on the shellcoding challenges.
I had no problem with buffer.
Yeah.
I only had it on 3 and on Unit U.
All right. So if you do that,
Did you use
F-sync.
sync.
F-sync.
Yes. Thank you. F-sync. I think. Is it F-sync?
I mean, I guess you could go through how you find out.
No, it's the C that does buffering. It's not. Yeah. It's not. It just calls it to buffering.
So you can. Pipes can buffer as well, depending on how you're launching this
That can
thing.
be internal.
It's a buffer on the pipes.
I.
You're syncing it right to the display.
Yes. So this is kind of a black magic that I am not 1,000% familiar with. I do random stuff in this until something works. In this case, this just worked. Generally speaking, you'll have better luck using tools made for the job than catting stuff in and out of a program. Cat definitely buffers, for example.
I had an issue that I don't know if it's buffering related. I was trying to do like a 2-stage thing where I would just, like I had a shellcode that would just call read into the instruction pointer from standard in. And like strace was showing that it was making that read call, but it would always return read 0 bytes and just kind of have like an empty string. And it would just do that immediately. And I was able to, that was with, I tried catting that initial loader in, and I also tried, I don't know what the word for it, if it's like redirection where you do like the less than symbol in. Yeah, I tried using FIFOs too, and it
Where you were trying to read, right. Because I ran into that on one of them, where I was trying to write to a
Yeah.
memory area that wasn't.
no, I don't think it was,
Writable.
I didn't have anything like that. It was just that the actual read call just immediately
I think that's what.
What was the return value?
0.
Check
At least for me.
Were you sending all the data at once of both stages?
No, I was, well, I sent the little loader shellcode all at once.
How are you making sure that they were separate?
Oh, it was literally like, it was a separate file. I mean, I had one shellcode chunk that would just call read into the instruction pointer. And that got loaded, like, and that was another thing, it's like the disassembly, it got loaded in fine. And strace showed that it was making that read call, but it wouldn't wait and prompt for input.
How were you sending the follow-up?
I tried it through Pwn Tools. I tried it just catting and redirecting just in terminal.
So with
How did you
Pwn Tools,
cat into it? How did you cat the follow-up? Because the first one would already require.
Right. Right. Yeah. Okay. So in the case of when I used cat on terminal, it was I had to use like a FIFO because otherwise I wouldn't be able to. There was no. I can just type in my shellcode. But I also tried with just Pwn Tools. That's how I was doing most of it.
So you're doing Pwn Tools.send, and
Yeah.
then Pwn Tools.send again immediately?
No, and then I would read until like executing shellcode because I was waiting.
And
for
then you
prompts.
did Pwn Tools.send.
Yeah.
That
so
should
I
work.
had to, what I had to do was use interactive.
I already know the lib sequence.
I had to set it to interactive, so send the first payload, set it to interactive, and then I'd wait a second or two, control D out of that, and then it would automatically, send the second payload after that, and then it worked.
So
It's like you had to wait longer than.
So even just
I don't
reading
know.
up
Sleep
to-
might have worked because we couldn't read the full buffer because the buffer was one.
guys, let's move on because we can be sitting here talking about this for a while. We can look at it during a break or after class, or tomorrow in office hours.
Slow.
Yeah, tomorrow in office hours.
I didn't see it.
But the bottom line is, please make things easy on yourself and use the right tools for the job. Echo, cat, Control V is just gonna make your life more and more difficult as time goes on.
Just out of curiosity, do you know if cat uses one atomic write or multiple different write syscalls? Because if it's multiple write syscalls and something happens to read because it received data and that's all there was, then it could also be something.
Cat will do a write. My understanding, cat will do a write on the whole buffer. No, I think cat might be line buffer. It's not impossible. Maybe not.
That might mean that if someone sends shellcode with an address that has like 10 or something, right? Then it's going to send only part of that shellcode.
Yeah.
Then the program's going to accept that as the entire
Yeah.
read, and then cat
So you have to
will
be
send
very
more.
careful that the way that you're sending things is sent as atomic as possible, because your shellcode isn't chunked up. Because if a program does a single read, you send your shellcode in chunks, it might only read the first part. It might also, depending on how data makes its way through from where you're sending it from, through the kernel to the program, might read more than just one chunk.
One of the later challenges, I think it was 11, talks about unpacking more shellcode into your program. I kind of got stuck on or hung up on how to do that. Could you kind of give a brief overview?
Sure. So, you might have a situation where certain bytes are not allowed, right? So let's say, for our example, let's say SH is not allowed in terms of shellcode, right? So we have or let's say the word flag isn't allowed. If we, wait, that's wrong shellcode. We have /flag here. So if a loader doesn't allow us to use the word flag, but otherwise we can write shellcode that we want. We can write flax, which is a very healthy seed. And then in the very beginning, we loaded RDI. What's up?
My question stems more from like if you have a ST like an input buffer that is of a very very small size,
Uh-huh.
and you somehow need to input a shellcode that is larger than that.
Yeah.
Because I was like, that's Prom 11 has a restricted buffer size.
Yeah.
And yet you have to execute shellcode that should be longer than that.
Right.
And so it's kind of how to insert it.
So in that case, anyways, let's cover this case since I started. Is anyone interested in this case? All right. So you have a /flax, and you need to read /flag. The challenge does not allow you to input the word flag. Let's say when you load the address of the string, you could simply move into RDI plus 0, 1, 2, 3, 4. the letter G, and now you fixed up flags to flag. If the shellcode is writable, then you are good to go. If you compile the shellcode, you're right. Okay, that was my make file that compiles everything for this class.
You use header files. Never use header files.
What?
Never use
Oh yeah, that's boring.
declare.
I use header files for the defines, the necessary defines. So that shellcode, if we strace the test file that was generated, it just crashed, so that's not good. What happened? Move B RDI plus 4. G, all right, well, GDB, send file md64.elf, run sigseg in start.
Oh, it's because you did the address instead of.
No, this should be correct. We have the address of the string,
Oh, you did that.
and then we,
You said RDI?
no, it should be fine. Oh, no, it still should be fine. All right.
How sure are you that not asking writable at that point?
Yeah. Because you shouldn't have write execute.
Yeah. Stage protected.
Oh, because I'm compiling it. Yeah. Okay. So yeah. So this is harder to test when it's compiled into an ELF. Of course, this is in the text segment of my binary. It's not writable, but it has been extracted also into this send file md64. So it's ready to be fired off into our shellcode, and I'll show that it works. It's the same one. Run it, and it works. So we can see here. It loads the RIP plus 2F. This ends up pointing right after the syscall to the word flax. And then it updates the X to be a G. And all is good.
So, do you have any idea why one of the challenges it's set and put down XYZ as the bytes and disassembled properly, but then it actually executed something completely different?
I'm not sure. That one I didn't have a chance to look into. It's possible that something in the code clobbers it a little bit, and you have to adjust.
No.
Then I do not know. Okay, so then, Connor, you asked about how do we go from a short shellcode to a longer shellcode. We can do this as well. So, what's your name? Regan suggested this already. So if you do send file md64 into something, read more, 64.s. All right, if you assume we're running at whatever instruction, if you're running in writable code, a writable code segment for whatever reason, we can load RIP into RSI. Can I just do this, or this doesn't work? Yeah, you need to do a relative load. Yeah. Then now we know where, so we want to execute fundamentally a read to read more shellcode over the next instruction. We get the return address, or the address of our instruction pointer. It might work. We might have to put a 0.
You write it. What effective address?
Yeah, should work. We'll see if it works. Then XOR RDI. So if we read from standard descriptor, or from file descriptor 0, standard input, we move RDX to be enough. We move 0 here to do a read, and we do a syscall. This then reads in more code and allows us to immediately start executing it.
You can just put an effective address into RSI. What's it referencing?
So the effective address when we're in this function, RIP always points to the next instruction. So when we're here, or when we're in this instruction,
It's not gonna return to the right place here.
Yeah, you'd have to add a
We need to add
return or
something
add a
to
label.
RIP.
and
or I
return,
can
right?
put a bunch of knobs when I'm giving my second stage shellcode. But if, okay, so what was pointed out is if we do this, then this will end up starting the write from here, and I'll actually overwrite stuff I've already executed, and then essentially start executing partway through my second stage shellcode. Does that make sense to everybody? Or do you want to run through it in GDB?
Run through it.
All right, let's run through it real quick. So, let me add it to my makefile. Oh yeah, it's not very comfortable. I could have sworn this used to be taller, or maybe I grew.
Yeah, you did.
It's possible. Okay, so let's see what happens with the when we execute it. Of course, page is still protected, so we won't be able to properly read, but we'll see that it is trying to read to whatever address our executable is at. So we are reading something. Let's see what happens when we do this on one of the challenges from class. Let's say the very first one. Shell dude, baby shell. Oh. Where the fuck are they? There they are. So here's baby shell 1. Baby shell 1 will read our shellcode into this. All is good. Let's just run it. And we will pipe in read more AMD64. Cannot insert breakpoint 1. Why? Oh, it hasn't mapped it yet. So we have a kind of complicated debugging situation. Did anyone run into this?
Yep.
Or it hasn't mapped the shellcode yet, but now we still somehow have to debug it. It's a pain in the butt. We can, of course, break in main. Delete 1. Yeah, or right before the jump, we run. Yep. Then we step next. Eventually, it'll jump into our shellcode, and so on. Huh? Yeah. So we can break right here. Continue. Here's our third breakpoint. Do next instruction. Now we're in our shellcode, right? What?
You have to step, because when you do next instruction, you'll step over. That's why you say voltage.
Oh, you're right. So, anyways, obviously this is a pain in the ass. So if you can do something else though. If you want to debug your shellcode, the way that GDB debugs is it replaces instructions in memory with a special instruction that returns control to GDB. Right? So you can trigger this instruction yourself. The beginning of your shellcode. Or not. You trigger the instruction yourself. It's the third interrupt. You're not going to go into what interrupts mean right now, but it is the third one. You run it, and suddenly it drops you into a debugger right in your shellcode. You can use this to stop partway into your shellcode to figure out what is going on partway through your shellcode. So here is our shellcode that loads our IP and so forth and does the read. Let's say we're confident that this is all correct. We just want to stop here and examine the state. Do that. Boom. We have a debugger. I didn't rebuild. Boom. We have our debugger. Great. We're about to do a syscall. Let's see what RDI is 0. Our SI is some thing in our buffer that is currently pointing to XOR RDI RDI. And as someone mentioned, XOR RDI RDI is partway through our shellcode. So if we get something like right now, reading in shellcode, and we read in to there, we need to make sure to send garbage up until after the syscall. Does that make sense? Okay. Does that not make sense to anyone? All right. So how do we solve this situation? Of course, we can say, okay, fine, do RIP plus whatever, however many bytes this is, calculate it out manually. Or you can have the assembler do it for you. Right? You can say stage. And here you just do a no-op or whatever. And here you do stage RIP. It automatically calculates this offset. And it'll load the correct value into RSI. Compile this shellcode. Run it. We left the interrupt in there. Let's look what RSI is. RSI is this. That's where our NOP is. And that's where our stage 2 shellcode will be written. And that is where, after the syscall, the return instruction, or the instruction pointer will go. Cool? Let me show you that this works. We take out the trap. And now we can do a 2-stage thing where first we'll do read more. And let me show you that this does not terminate. It sits there waiting. So we can do exactly what Regan was saying and read until, is it capital executing?
Yeah.
Read until executing, and then send our next shellcode, which is send file here. We don't need to ljust or pad it or put the return address because you're already running the shellcode. We just send it. And it doesn't work. What didn't work? On the read. Yep, it's trying to do read until. There's a handy tool handy function that'll let you give it a timeout, and it'll just give you everything that happened until that timeout and nothing happened until that timeout. Hold on, let's run this thing manually. I'm using a teaching one. It should work, right? It said about to execute. It's not capital.
Oh, sorry, the other ones.
Boom. Cool?
Actually, you can set debugger prompt that you were.
Oh. So, let's go back to the broken version. That's this one with the capital E. Hit enter. It's waiting for us. We're stuck. We hit Control C, and we trigger keyboard interrupt, which in Python just kicks you out of where you're executing. In IPython, which is really nice, You can do debug, hit enter, and you're in a debugger shell in the exact moment the keyboard interrupt or some other exception occurred. Cool? And then you can just walk up the stack chain, the call stack, and then inspect whatever you need to inspect. Cool? Very cool. Awesome. Okay.
Maybe show them really, really quick how to do that when you're not in IPython with the debugger call, the function call.
Dash.
I can't remember off the top of my head.
Okay, yes. If you want to do your so this works, right? Let's pretend that we weren't running it in IPython, that we were misguided, and we made an actual script, so that you can maybe repeat it when you need it to, and so forth. So of course this works. All right. What? I don't know what that was. But let's say this does not work. You call it, and it hangs. So you control C it, it does the keyboard interrupt, and then it quits on you because there's no interrupt, there's no exception handler for that. There are two options here. One is, the one option is you can say import IPDB is the interactive Python debugger. And IPDB, actually I doesn't stand for interactive, but it's fine. IPDB.set trace. And it drops you into debugger right there. Or dies. Let's pip install IPDB. Yeah, you can do PDB, but it's lamer than IPDB. IPDB has color. Boom, right here. Same sort of thing. Of course, we're at the top of the call stack right now. There's no farther up. But we can do stuff like step. And single step through Python. And at every point, now we have a call stack that we can go up and down. It's just a debugger, very similar to GDB for Python. Helps with debugging. The other thing you can do, and I actually do this as a catch-all, if you do IPython --PDB, and there's an exception, including a keyboard interrupt, it'll drop you into debugger immediately. So that's very useful. What's up? Oh, I thought you had your hand up. All right, cool. All right, let's move on. That was difficulty number 1. Difficulty number 2, and there were, of course, more difficulties. One of them we covered, which is modifying your shellcode. Third one was ingesting more shellcode. But difficulty number 2 is garbage bytes in your shellcode. There are times when there are restrictions on certain bytes in your shellcode. Can someone name one of those times?
All bytes must be unique.
All bytes must be unique.
Some monster decides to sort your shellcode.
Someone decides to sort your shellcode. You don't have full control. Sometimes you will need to say, okay, I am giving a, this byte is a sacrifice to the shellcode filter. I'm not going to control it. I'm just going to set it to something that will make the shellcode filter happy. There's a number of ways that you can survive that. One of them is something like this. Let's do this one. You have a stage 1, stage 2 situation. And there is, you know that the byte after this needs to be a certain value. One way is to make it a certain value and just jump over it. Okay? If you do a make and we execute the shellcode, does it? Let's find out one that worked. Okay, if we executed the shellcode and we scroll all the way up to disassembly, that byte literally made that byte. So here we do a jump over 1 byte, and here we have that FF, and capstone failed. Of course, capstone doesn't follow these jumps. It'll get confused, but that's fine. You can see the FF, and when we actually execute it, it'll jump over it. Obj dump is a little more intelligent. So we can do obj dump.
Wait, but is the code after all the bytes? The code that was underneath that byte?
Yeah. So if you obj dump -d, you can see here's the jump to after, here's a byte, and here is the next thing. If you notice, this is a very bad disassembly format. I apologize. Here's the correct disassembly.
It might be going down a rabbit hole, but it might be useful to show people shell pass ASM, because at
Yes.
least that way you can take the length and stuff really easily.
Sure.
Wait, what was the point of the jumping over?
So
Byte jumping?
if there's a situation where you cannot control that byte, this is one way of avoiding it. So you have a byte that you cannot control in your shellcode. It needs to be a certain value. You can jump over it. You sacrifice 3 bytes, but the byte you don't control has no impact on your shellcode.
What is the byte you don't control in this?
Let's say you were running an example that said the 9th byte of your shellcode has to be OXFF. Right? So we say, okay, fine, it's OXFF. Before that, we put a jump 1 to jump over it.
Oh, okay. Yeah, okay.
Yeah.
So like before any mangling or anything, it'll only accept it and load it if that's there, but that's not
Exactly.
instruction.
Yeah. That's one thing. There are other things other than jump that make it irrelevant. A lot of other instructions that you can get through whatever byte, maybe make it part of an instruction without bothering, without having it impact the functionality of your shellcode. Zach pointed out one useful thing is shellcraft. So if you set up Pwn tools for the right architecture, and then you can assemble stuff in IPython. So you can do XOR RAX, and it'll actually assemble it properly. Okay? You can, it assembles it exactly this, more or less the same way that I gave you as the example to build shellcode. It makes an assembly file, it assembles it, and then it uses copy to dump it. And gives you the results. So you can use this to check the length of certain things. The length of this instruction is 3, for example. Cool? Very cool. Okay. We're now going to move on from shellcode. So homework is still open for those that need to continue. I will push a couple more interesting shellcode cases I didn't have time to finish before this crazy rush to the deadline last week. And a couple of, as I'll discuss, a couple of things from homework 7 if you want to amortize the time you'll need to spend on that with any spare time you have before.
What do you mean, push a couple things from homework 7? Will it be in homework 6 was very related, or will you actually push homework 7 themselves?
We'll probably either push it to homework 6 but have it count for 0 points, or we'll open homework 7 early with some challenges. But homework 7 will be officially assigned, let's say next week, due the week after.
So now that we're not going to have homework 7 due next week, does this mean we're only going to have like 14 homework 7?
Yes. Yes. That is correct. Okay. Cool. So, with homework 7 not being assigned until next week, we have kind of 2 weeks to cover advanced exploitation scenarios. Oh, right. First, I want to give a shout out to the master hackers up here in alphabetical order. We have Dasher, a astronomer up there, a philosopher and astronomer. Precitator Will, and Ponish.
I saw also IO, somebody?
Yeah, IO
The auditing?
is an auditor, or not even an official auditor. He's just crashing. And then there was someone else too. Oh yeah, God. Cool. Hopefully everyone had fun with these things. Shellcode is my favorite category. Did anyone get stuck on 3 and not move on to 4? Because 4 and onwards, they don't really use that the thing you need to do with 3. 3 is the only one that forces you to actually compute or figure out the return address. Okay, let's get through the intro of ROP, and then we'll take a break. Or should we take a break now and then do ROP? All right, let's take a break now. 15-minute break at 7:20. We'll start in on ROP. And we are live. Okay, so we're going to talk about return-oriented programming today. And by the end of the day, or really by the end of the assignment next week, you'll all become return-oriented programmers. So the story so far is this. With homework 3 and 4, we, or I guess with homework 3 and 5, we explored reverse engineering of software, right? You opened it up in OBSDump, you try to understand what it does, you find weaknesses in it. Homework 4 and 5, we started redirecting control flow, causing the program to do what we as the attacker want to do. And with homework 6, you've now explored the injection of code into the program when the program doesn't already have the functionality that you're looking for. So far, this has required 3 things. One is access to the binary code to understand what's going on. Of course, some of the teaching challenges you can get by without actually looking at the binary. But realistically, in order to exploit something, you need to have the code on hand to reverse engineer and test with it. Normally, we've required something like knowledge of your shellcode, knowledge of where stuff is in memory, knowledge of addresses, of what's going on in the target process, and the ability to execute shellcode, right? So in homework 6, all of your shellcode was executable. All of the memory where your shellcode was stored was explicitly made executable for you. So we're going to go through and today see what happens when these assumptions are violated and when the actual real situation is different. We're not going to make it all the way through ROP today, but because we have this now built in flexibility with next week, we're going to make it through as much as we can make it. Like a normal class, won't stay over by 20-30 minutes into 9:30, and then pick up next week to finish this off. So what if we start violating these assumptions? So one assumption we might violate is that we have the ability to execute our shellcode. And we touched on this last week with NX, the no execute bit. So far, you haven't run into this. So far, all of your shellcode has been quite executable, and so forth. This isn't always the case. We covered how you might bypass the presence of NX using JIT and so forth last time. But the workaround that I want to showcase is that, and really showcase this as a lead-in into the concept of return-oriented programming, is the case where we can't inject executable code, but we can fool the program into making some other piece of memory executable. So let's do that. So I've prepared this demo. And it's called vuln1. It's gone. Nope, wait.
Did you resume the recording?
I did resume the recording. Thank you. It's not gone. It's in a different directory, just hiding. So if you have a bunch of different vulns up through 5, vuln 5 gets kind of crazy. I don't know if we'll have time for that. But so vuln 1 is a nice, simple program that has, let's do that with syntax highlighting, that has a buffer in the global space of the binary. What is the memory region where global variables are located called?
BSS.
The BSS. So it has some shellcode on the BSS, reads in your shellcode, and protects something else, a protect target that was set to useless, and then calls a call target that wasn't set to anything. If we run this, it crashes. That's very sad. If and why does it crash? If we demessage, it crashes at 0 because, whoops, because this call target, which is being called here, is not initialized. Okay? Can anyone read that syntax? What's happening there?
It casts the pointer to a function that takes in nothing, returns a void, and then call it.
Yeah. So I basically use that variable, vulnstruct.callTarget, cast it to a function pointer. This is the cast. It's a function pointer that returns nothing, takes nothing as input, and then I call it, and that's here. In the code, that is what creates, hold on. In the code, that is what creates our our call to RDX. Cool? So we have a variable and we call it. Okay. So this is kind of the simple case where normally it is not actually protecting our shellcode. It's protecting some other useless variable. If we inject shellcode, it will not be executable, but we can fool the program, I will claim, into thinking that the shellcode can be executable. How do we do that in this case?
It's just a guess, but maybe you could jump to where that memprotect syscall is happening, but use different register values somehow.
You're getting a little ahead, so we're gonna do small steps until we get to true ROP. Right now, we don't even have control over the return address from this function. We have this read. Everyone sees this read, right? And the read, why is there? And the read here reads OX 2000 bytes. And what's the size of our buffer? OX 1000 bytes. Problem is, of course, we overflow. But the issue is that we're not reading onto the stack. We're reading somewhere into some global memory. We're not overflowing the return address. No matter how much we send, we're not going to take control over the return address. And anyways, we do this call. So were you specifically talking about the return address when you were? Yeah. So we can't do that.
Just fill up shellcode and then overwrite protect target, call target.
Yeah, if you fill up shellcode, after 1000 OX1000 bytes, we're able to control the contents of protect target. This directly changes the page that mprotect will make executable, and we just point that at our shellcode. Our shellcode is at in the BSS, and this program is not position independent. You can see these hard-coded offsets. You can also see the fact that I named it -no PIE, which is telling. But also you can see that it says executable and not, as we'll eventually get to, shared object, right? If it's relocatable, if it's a position independent executable, if you recall, it says shared object, it says executable, it means we are in not a position independent executable. So we can actually test this by launching it. Catting the mappings, and you can see it here. Obviously, this does not look like a random address. This is one of the standard OX400 of non-position executable stuff. If you want to see what, as a reminder, a position independent executable looks like, we do that. Why are there two of them? I know why there are two of them. If you look at one of them, 6244, that's more like a random address, okay? Everyone has had painful experiences with position independent executables here, right? Who here has been untouched by PIE pain? Good. I would be worried for your grades. All right. So, I forgot why I went into PIE. Okay, right. So, the reason we did that was because it is not position dependent. So you know where in memory the binary is mapped. You know where the global variables are mapped. The global variables are mapped. We can see roughly where. Again, by doing this. We have the code is mapped here. You can see it's readable and executable at 4000. And of course, if you remember when we looked at the object dump, it gave us the same location. And here we have a readable and writable mapping. And we can, the BSS is somewhere in that mapping. Cool. Okay, so what does this mean? This means that we are going to read into the BSS. If you override this and point it at the BSS, we'll fool mprotect into setting our shellcode as executable instead of the useless bytes. And then we will execute our shellcode because we can also overflow the call target to point to our shellcode. Cool? Everyone on board? Awesome. How do we do this? We start with our shellcode. That's our shellcode. Slightly modified to not have the word flag in it. We're leaking flags. Or are we? So we run vol1 no PIE. We cat the shellcode in it, of course. This is not the hacker way, but we'll just be lazy for a sec. And it's sec false, of course, because it read in the shellcode and protected something else because we didn't do the overflow, and then called something else because we didn't do the overflow. So let's just do the overflow real quick. So we'll actually, let's grab the scaffold here. So we'll open vuln1 dash null PIE dash AMD64. I don't know why there's a non AMD64 PIE. Won't read until anything. We don't need a leaked address. We open send file AMD64. Read it. Justify it to X1000. And then afterwards, we have X1000. Afterwards, we have the protect target and the call target. And let's just 41, 41, 41, 41. That's one address, and then that'll get overridden into the protect target, and this will be 43, 43, 43, 43. This should be the call target. Okay, does that make sense? Brilliant. So that'll of course crash because those aren't reasonable places, but we will see what happens. So if we launch it, boom. Okay, presumably it crashed. We can wait for it. How do we get the return code? Anyways, it doesn't matter. It crashed, and we can see in the message that something weird happened. Yeah. So let's strace. Phone process requires you to give a list of the arguments if there's more than one. Boom. So now we did mprotect at a strange location, so that's not 4141. Oh, all right. So why is that not 4141, 4141, 42, 42, 42, 42? I heard what?
Isn't it just the page, so the last three?
Exactly. It is just the page, so that's what this garbage is right here. We AND it with the inverse of FFF. So we zero out the last three nibbles. And why do we do that? Page alignment. So you protect and map memory on a page by page basis. So when we do the protection, we need to do it on a page. And then presumably if that was correct, then this is probably correct. mprotect errored out with enomem because there is no such memory. Sad but true. So let's do this. Let's grab the address of that read. Easy. What's the correct way of getting the address of the read? Looking in GDB probably. But there's an easy address, or not the address of the read, but the address of our shellcode. Look in GDB for the read, see what gets passed in. There's an easy way. If you have an strace, we can see the read here. And if we turn off all, does anyone remember off the top of their heads how to turn off strace, putting this as a string and have it as an address instead? Dash what? Dash I. No, that's the instruction pointer. We can also just do that. Put it in there. Dash X will give us the so that'll give us the string in hex. That's not what we want. Right, so now we have the string in hex. That does make it easier to deal with, but we want it to give us the address instead. We can do it. How do we do it? Okay, output format. Like 12% of hacking is looking at man pages.
Try dash E.
Dash lowercase e? No, this will modify the event.
Raw equals read.
Yeah, E raw equals read.
So s trace raw equals read like this.
Dash E space raw equals read.
Ah. Brilliant. Boom, we have an address. So this is for cat. Where's this address? Somewhere it's either a mapped memory or in oh yeah, it's mapped yeah, it's mapped memory. So it maps some memory right before it and reads right into it, and it maps a ton of memory. So now we know that cat memory maps memory to read into. Anyways, that's not important. What's important is we can do dash E. Dash E raw equals read. We have our address of our shellcode, and now we just put it here, and boom. Let's take out strace. And boom, and here's the flag. Okay? So what did we do? We wrote in the shellcode. Because this read read in too much, we overflowed protect target and call target. The program did mprotect on the protect target. So we triggered the program into calling mprotect on our shellcode, and we jumped to it. This is kind of like early Christmas, right? Because the program is just wanting, just needs to be slightly convinced to give us shellcode execution. But of course, real programs aren't like this. But this is simple mprotect demo. So this is one workaround for an X, but not a very realistic one. And realistically, we need to do something else to deal with it. And what the world has kind of moved on to from shellcoding in most cases, unfortunately, is return-oriented programming. You already did some return-oriented programming in homeworks 4 and 5. Who here did the example where the win function wouldn't let you win if you didn't pass it the right argument?
Or you could be insane.
You could do two things. You could be insane and figure out how to get that argument into the correct place, or you could jump over it.
You could rock too, because they get the correct argument.
So let's look at the jump over it case, right? Who here solved that one with a jump over? Awesome. So I wrote it here as vuln2.c, and it's a very simple thing. It reads in a bunch of stuff, compile it without position independence, so we know where the code is, and it simply jumps into. It simply allows us to jump into win, right? So this is nice and simple. Let's recreate it. So here's vuln2 no PIE, no shellcode necessary. We send 128 A's, and then plus a packed. How do we get the address? I'll just do the normal sane way.
Why do you not just have outcome failures to outcome dash m?
That'd be a good idea. Anyways, let's see where the win function is. It's here. We put in 40641. Multiplied by, I don't know what's a nice big number, 20. Boom. And it Didn't do anything. Hmm?
We need more. How are we doing?
20 is quite a lot. Volume 2 dies in libc. Why is it dying in libc? I did not expect this part to be complicated. Alright, so nice thing here, we can oh yeah. We'll save out the payload and debug real quick. Oops. Why is it all spaces? What the hell?
Maybe when you did that adjust.
No. This.
Should just be A's.
Oh, sorry. It's the blah file. Okay. Here we go. It died in sprintf. Oh. Oh, an assert fail. Ha. Ha ha. That's funny. It okay, so we did it. I'll explain what happened. Do you remember when I said that if you trigger an assert fail on the stack canary, we can control the data that it prints, because assert says, hey, this code failed, or at least when the stack canary is violated, if you remember, it says stack canary failed for : unknown. It used to print the program name. Why doesn't it print the program name anymore?
Because you could change wherever that program name comes, you could change the data to point it.
Yeah. So it used to get the program name from the stack. If an attacker controls the stack, suddenly when it tries to read the program name, you control the pointer that it dereferences to read the program name. Because it would read argv 0. Argv is a pointer on the stack. So that behavior no longer exists, but assert still prints this line failed, right? And when it prints that, actually it must use the stack in some way, and we are overriding it and it's failing. So
Can't that be determined to compile time?
yes, it should be. That's why I kind of paused. But for whatever reason, we're failing in assert.
What's the C code?
Yeah. Is the secret of it?
Yeah, in the win function.
Are you sure you're jumping to the right place?
Yeah, we're asserting this. We never
Yeah.
wrote that.
So let's just trial and error experiment here. 2 is too low. 3 is too low. 4 is too low.
Are you sure you're jumping past that check?
I'm sure I'm not jumping past the check. I want to make a point. Oh, we're still triggering an assert. All right. Let's avoid this check for now. For whatever reason, we're unable to trigger the check or to actually survive the check. So what we did, and what you all did, with Vuln 2, with it was the DOS binary.
So what's going on here? We're hitting this assert, so we didn't put the win value.
We didn't put the win value. But what you did when you solved it, presumably, was just jump over this check.
Yeah, that's right.
Yeah. So
Well, we did it both ways.
you find where it calls assert fail, and you just go here, and here's the flag, right? So it was very simple. We jumped partway into the function. And the core takeaway, and specifically that was right here, after assert failed. Who knows what it's doing here, but we know that this is after assert failed, most likely. It's a good, worth a try, and it happens to work. What we basically know from this guy is that you are not restricted in overriding the return address to point to the beginning of a function. This makes sense, right? The return address almost never points to the beginning of a function. In fact, would it ever point to the beginning of a function?
Yes.
What?
I did tail call optimization.
Would a tail call?
I would just do a jump though.
Yeah. So I don't think a return address, don't quote me on this, I'm kind of fried, but a return address should hopefully never point to the beginning of a function. But when we were playing with the win function, that's kind of the mindset that we got into up until DOS. And with DOS, we were suddenly moving it, pointing it to other places. So I have 2 demo times. Let's see what our demo is in store for us. If we look at Vuln 3, okay, so I think that first demo was going to be Vuln 2, which we already did. I'm going a little out of order. So obviously we can jump past the check. What if the program was less nice? So what if, unlike Vuln 1, where we had a shellcode, our shellcode that was protected almost perfectly for us, and then jumped to, we have Vuln 3, where, hold on. What if we had the case where we have a program that isn't really meant to protect anything to do with our shellcode? There's just a protection call somewhere that happens to exist, but normally we don't trigger it. So in this program, we would read our shellcode, and we'd return. And we read our shellcode, onto the stack, and return. I have a feeling that I overrode my Vuln 3 with Vuln 4. Shit. No, okay. Yes. I think we'll deal with it. So, let's see what this Vuln 3 does. Can't be that bad. Yeah, I agree. All right. It's a protest. The suffering is a protest. So here's our program. Nice and simple. These 2 functions. One of them loads in our shellcode into RAX, calls read, EDX, the third, or RAX gets put into RSI, the second argument to read. The first argument to read RDI is 0. Third argument, RDX is 2000. We call read to read in, or OX2000 to read in OX2000 bytes into our shellcode buffer, and then we simply return.
You
There's the leave instruction. Does everyone remember what the leave instruction does? You were almost raising your hand.
Yeah, it recovered the frame.
It basically releases the stack. So this reserves OX 1000 bytes on the stack, shifts the stack to the left by OX 1000. Oops. This one undoes what this did.
How does lead know how far back it needs to?
Because we saved our RSP into RBP. RBP is the base pointer. So sorry, it doesn't undo this. Fundamentally, it undoes this.
Okay.
Yeah. And then it returns. Okay. So how do we exploit this? We can just overflow, put our shellcode, overflow our shellcode. I remember what I was going to do. Okay. Put our shellcode on, overflow it, the return address, return into our stack, and everything is happy. In order to do that, of course, we need a leak of the stack pointer, which is the easy route. So let's do that. I was going to just disable address space randomization for the course, but that's lame. I just decided. So we have a leak.
You're gonna do full val round now or partial val round?
It's irrelevant for this.
Maybe for this one.
Right. So
Of course.
now we have Vuln 3, no PIE, AMD 64. Boom. That's where our shellcode will be read into. We write that shellcode. We write two more things. Overflow the return address. And all is good. So the trick is what?
Rewriting the source code.
Exactly. Okay. We don't have to do this. We can. Let's make this a little harder for you. All right. So it's I disabled PIE as well.
Or not SLR, but are you still getting?
Yeah. So
I was thinking of the stack layer.
I also disabled the secondary. This is base case. Let's do it for real. So I'll show you that I took that print back out. I've repented. ASLR right now is on, but we're not going to be able to exploit it that way. So we're going to turn off ASLR. This is a secret invocation that disables ASLR. But if we run a shell, now everything under the shell is disabled, ASLR wise. Cool. So now, if we strace this guy and see how it's reading the shellcode, here is the read, and here you can see that doesn't look very random and is the same every time. So we're gonna assume that the stack is not randomized yet, or that we're getting a leak in a similar way to level 3 of the shellcode. So how do we proceed? We open the Vuln 3. We create a shellcode of our shellcode. Send file AMD64 dot read, and then we send the address of where we're going to be reading to. We need it twice. What happens if we just do one? What do we overwrite? The base pointer. where was our ops dump dash Intel? Thank you. Vol 3 NoPy AMD 64. So here's the function. We have OX1000, and then to the right of that on the stack, we have the saved base pointer, and then we have the return address. So we need to put two things. Actually, what we put in the saved base pointer, in this case, doesn't matter because it doesn't use the, it's libc saved base pointer. If you remember, libc doesn't use the base pointer for anything important. So if we send the shellcode, we read, this will put shellcode in the stack, jump to it, and we get the flag. Except for we don't. Why don't we get the flag? Because if we GDB this, it's the base pointer. What we're overriding the base pointer with. And we can just override it with the same address. Alright. So we wrote blah again. Yep, there it is. GDB vol 3 no PIE. Cool. We ran it. And it didn't crash. Why didn't it crash? Because I did not adjust it to OX1000. Alright. So, we run it. It crashes. It crashes here. Why? Not because... What the hell? But that's not what I sent. Yeah. It is writable. It's on the stack. Oh. 560. It's not executable. That's what I want to show. But it is also not correct right now. Oh, it's a bunch of spaces. God damn it. All right, let's hold on. Let's adjust it with a different thing just to make sure. Okay, GDB, boom. What the fuck? Yeah, I agree. So what the fuck? Maybe. See, S trace. I mean, that's where it's reading to. Yeah.
So the file's empty?
The file's not empty. Let's see what's going on. So RSP. Let's see what we overwrote. All zeros. Yeah.
No. The other file, the one you're reading, the open. The sim file and
Yeah. Yeah. This is what gets logged. So this is shellcode. And here's my /flags, a healthier version of the flag. So what the fuck is going on?
Running your code until it hits the zeros. Running your shell code.
Because it shouldn't be executable.
It's not executable, and this is the target of the read call. So, and if you look at this -4, the fuck is happening here? No, but here's, okay, let's look at, 48 is H, right? Yeah, this is my shellcode somewhere else.
It's C500. Why do we end in 560?
So if you S trace it, it's reading to C560. Does everyone agree?
Actually, I mean the 500.
Actually reading to 500.
Because that's where we saw your code.
I agree. Why?
See the source again.
Because GDB is setting it different. When it turns off ASLR, it's doing it different. Go to the break at the read and
You're right.
Genius.
Genius. You're right. So we ran into the exact problem that I warned you guys about. See, no one is immune.
run into that if you do the GDB from home tools instead of the GDB attached.
So there are a couple of things going on. One is we didn't disable ASLR for our IPython shell. So we're going to do that now.
Just echo T rock.
Now we can S trace this, which should be okay. All right. Here is our correct read. It changed between the different runs. Yeah.
Now it's 360. I'm just saying you have to change it in the code.
Yeah, we have to change in the code. We'll accept that mystery. Okay. So let's keep going with this. It reads OX1000. Why the fuck does... Wait. Oh, fuck. It should be 1.3. Man, this is a comedy of errors here. All right, 1.3. Why is it a third number? We'll take that. All right. Now we read things, and now we were crashing at E0. Okay, we're actually jumping to our to the shellcode, which I guess we were before, anyways. So cool. So things are crashing because our shellcode is not executable, right? And this is going to be quite a pain to debug. So let's do this.
Oh, you can do the home process. You can ASLR false.
Sure, I disabled ASLR for the whole IPython shell. What we're going to do is, before sending it the payload, we're going to wait for input from the user. So now it's waiting for me to hit enter on that shell. I'm going to attach to it. Yeah. And you won't be able to disable it for set UID programs. Obviously. Actually, that would be worth a test because it won't drop set UID. It's not a... You're still running it quite natively.
From what I'm aware, you have to use proc if you want to disable it for set UID.
I see. So in the Docker, you can't...
It could be wrong.
I've only ever done it in a privileged Docker. Let's find out. Do we have set arch actually by default? Yes, okay. Yeah, you're right. Never mind.
You can't do set arch inside Docker because you're not running the privileged one.
I guess. You're missing some permissions. Probably if I run it as -- privileged, it'll work.
Does that mean clone
Or it'll definitely work. I was doing it yesterday.
Does that mean the clone tools, if you say disable ASLR, will also not work?
Probably.
How does clone tools?
Probably the same way. If I had to guess. Okay, anyways. We will... Try to recall the correct syntax. Ten, 817. Thank you. Now we're in read. Okay, here it is. Now we continue. Hit enter here, and we crashed. That's our shellcode. Everyone recognize it? It's beautiful. It'll read the flags. Okay, so, and of course, if we step, it crashes. Why? Not executable. The stack is not executable. Luckily, the whole point of this very painful exercise was that there is something that allows us to unprotect the code. So we can jump to unprotect. Instead, so if we do our opt dump, we have a happy little unprotect here. And if we just jump to the protector before returning to our shellcode, we'll be good to go. So how do we do that? We can jump to the protector, right? That's easy. So we can change this to go for, instead of to where we know the stack to be, to go to the protector function, right? We did that. That's easy. But how do we get the protector to return to our shellcode afterwards? How do we keep control?
Does it have something to do with pushing values to RSP and RVP? Because when they pop, you can know what the return value of the next return will be.
You can control what it'll be. So here's what we can do. Let's say we write the return value that is immediately after that main will return to. This, everyone understands how we control where main returns to, right? We override it on the stack. Suddenly, we're executing protector. Protector, after doing all this stuff, is going to return to the value stored on the stack. And it thinks that the value stored on the stack was stored by whoever called it. So if main had called protector, it said, okay, main took care of storing it on the stack for me. I will just read it off the stack and return to it. What if we store it on the stack for protector? So let's put a bunch of A's and see what happens. So same sort of thing. We hit it. It waits for us. We GDB. We attach. How do we...
Did the process already die?
No, the process is alive. I'm just trying to remember the syntax. There's a way to do this. Bang? Fuck it. So first, this is correct, right? Be careful. Yes. Can we do... No. Can we do this? Okay, I give up. We'll just do it manually. Attach.
We already have the number 8.
What? Oh, yes. You're right. Thank you. Boom. Okay, cool. So now we're in read. We hit continue here. We hit enter here. Now we're in the sec fault, but now in protector. Why are we in protector? We're at the ret. And where are we about to return to? A bunch of A's. So let's see what's happening here. Let's restart this. Let's do our fancy shell. Oh God, why? Restart that. Restart this. Now it's waiting. Fuck. Oh, it's fine. Okay. I exited the shell that didn't have ASLR, but we're okay. Nope, that's Vuln 2. Oh God. Alright. Here we go. Shell. We attach to this. We're in read. Makes sense, right? Let's hit enter here so it sends the stuff. And we'll just next I out of read. Okay, we're back in main. We're about to return from main. Where are we about to return? We're about to return to the protector, right? Because this is the address that we overrode main's return address with. Cool. Cool. So we do step instruction. Now we're in protector. And what does the stack look like for protector? If you called protector, what would the stack look like? Who started whispering return?
Return with S and then save DB.
If we called protector and then we looked immediately at the stack, we would see the return address from protector because call pushes the return address onto the stack. We didn't call protector. We returned into protector because we exploited the software. So as we wrote over the stack, the thing that is right after the return address from main is the return address from protector. Right? So now when protector returns, it's going to return to that controlled address. And then after, since it returns to that controlled address, that means that we can control a chain of executions. Not just one. So far, you have just redirected execution once. But because we control the stack here to an almost arbitrary depth, we can continue to control the return addresses of the code that we call to make it do what we want. So what do we want to do in this case? Protector will run. Protector will make the location right. What? I think I wanted to make it the address of X, so that's a little more complicated. But protector will do some cool stuff. It'll set up a call stack for a call site for mprotect, and it'll call mprotect. All right. So, anyways, everyone agrees with me that the return address of value, the stored return address in protector is 41, 41, 41, 41, right? So when protector returns, it'll return there. Let's step. So we're stepping, we're stepping, we're stepping. We do a bunch of stuff. We're stepping. And now we're calling mprotect. So let's step into mprotect. Where will mprotect return to when it returns? mprotect was triggered by a legitimate call instructions. So the call instruction, of course, pushes the return address onto the stack. When mprotect returns, it'll return to wherever that is, and that is the next instruction in protector, as it's supposed to. But if you look at the stack, this is where mProtect will return to, right? If we look at the disassembly, then protector will do a leave, which will essentially add OX10 to the stack, so it'll pop. So this returns, pop 1, 2, and then it'll return to the protector again. Why? So let's return from mProtect. Next instruction, next instruction. Where's protector about to return to? Okay, 41, 41, 41, 41. Right? So the point is, protector is able to continue functioning normally. It calls mProtect. mProtect returns to the protector. And after that, when protector returns, we regain control because we control protector's return address. Does that make sense? Kinda? A little bit? So, what does all of this get us? Let's relaunch. And actually, for everyone's sake, I'm going to re-enable phone debug. I don't remember why I disabled it the latest time. Okay, so we're in protect. We're GDBing again. We're in IPython. We run. We attach. Okay, here we are. Is that a little more readable? We entered the start, and we break in protector, and we continue. Okay, so now we have entered protector, and we've pushed the saved. Oh, that's why it was here. We push the saved base pointer, and then we have started execution. So we're partway through protector now. When protector, what does protector do? Protector will call mProtect. Let's walk forward to mProtect and see what it calls it on. Calls it on an address of 0. That's unfortunate. Calls it on a length of OX1000. And it calls it on a prot of 7. 1, 1, 1. It's exec, write, and read. What will this do? What will it try to do? Someone other than IO. What will it try to do? All right. Allow you to read, write, or execute. What page? Someone other than these front row people. Duffy. Which page are we trying to unprotect right now? 0. Yes, correct. So we're trying to call mProtect on page 0. Is page 0 mapped? No, there is no page 0 mapped. In fact, there cannot be page 0 mapped. For various reasons, modern systems do not allow you to map memory at low addresses. It's too prone to bugs like this, where this should fail, ends up working, you're able to write something to page 0 and start executing it. So, that's no good. We're aborting this run and we're starting over. And we're going to try to see how do we get, if we can get, because I'm pretty sure Vuln 2 got kind of fucked up, or Vuln 3 got kind of fucked up, can we get it to actually protect our shellcode to be executable on the stack? So we start up, we GDB it, do our shell, we do our attach, 11914.
Didn't you make the local variable, didn't you initialize it versus it was uninitialized before?
Oh, maybe I fucked it up. Anyways, don't worry about it. We break at protector. Continue. All right. So we are starting. We're breaking at protector. And what does protector do? Protector calls mprotect. Mprotect takes some very important arguments. This is important, and this is the critical one to make it prot exec. And then REX is the one that we need to we need to either set RDI. No, we need to set RAX somehow before getting here. We need to set RAX to be the value that we want it to be. Here, it moves something that's not very good into RAX. And that something that's not very good is this 0 here.
Well, you could maybe jump to that move instruction, or just overwrite on the stack wherever that will be pointed
To this move instruction.
That, yeah, because RBP will be from RSP previously, so you can overwrite
Right.
on the stack.
So this instruction reads some data off of the stack, stores it into RAX, and continues. We don't have to execute this guy. This is the guy that zeroes it out. What concerns me is that move EAX, we might not have enough control there. But let's see what the situation is. The situation is not that good. RAX is 0 right now. That's not great. So one thing you can try to do, as Zach said, if you fast forward to here, let's say the stack is all set up. What is RBP minus 4? It's zeros already. That's not good.
Well, what would it be if you jumped there? That would
If I jump there, that's right. Yes, then I would control that. Let's say.
Hold on, isn't, because it's in brackets, isn't that the address minus 4?
Yeah, the address. It is.
Address 0, I thought the address would be D3E4. No?
The address is D3E4. Yes, but
So then it's minus 4 of that address, isn't it? Not the value.
no. RBP is D3E8, and then
Oh,
yeah, at minus 4 is D3E4.
okay.
Okay. We have a problem. What we want this to do is call mprotect on our stack, right? Our stack is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bytes long, our stack address. If you're calling this guy, it'll only read 4 bytes. Read it into EAX, which is a 4-byte register. There's not enough there to store our
What if we change the source code back and revert the initialization? Did it-
maybe. What's up?
Question. Can we, like when we're in main, can we overwrite the return address to jump to our shellcode, set some registers, and then call like a specific address in here, or is that not
So
possible?
you're saying you set some registers in your shellcode?
Yeah, and then can you like call to a specific address in particular?
There's a bit of a chicken and egg problem because your shellcode needs to execute to set registers.
You can find a get
Right.
RAX.
All right. So let's move on to what can we do.
Does anything prevent you from rewriting that entirely
Yes.
If you can figure out the text coding to all the instructions that you need to run, overflowing on CSE466, essentially just enter those rights. And,
So that is shellcode, right?
right, exactly, but into the protector function. Because you want to call and protect on
There are
the
two problems.
shellcode, yeah.
One is when you're overflowing in the stack, you're writing to the stack, but the protector function is in the text section somewhere else. That's one problem. The second problem is that is not a writable memory address. So what do we want to do? One thing that we can do is we can find painstakingly in the program some other functionality that sets RAX to what we want, and then we jump here. So can we do that?
Are you going to give us another week? Or dash static?
Does the end of main have a move RAX return?
It has a move something into RAX, but what does it have into RAX? So let's see if there's an instruction that we can use. Disassemble protector. Disassemble main. So we have a move EAX 0, so we can 0 out. So if we jumped here, we would 0 out EAX, then we would return, and that's no good.
Could we find a pop? Because we control the stack, right?
Yes.
So if we find a pop and then return a pop EAX,
Yeah.
return, we would pop in the
So
That's what we need.
if you guys follow along with what people are saying right now, everyone is saying, hey, what if you find, since we can control wherever we can jump anywhere to any instruction because we have full control over the stack, let's find a little, and because we have so much control of the stack, after we're done executing whatever we jump to, when it returns to what we control anyways. Let's just find little snippets of code that do something and then do a ret, and then let's chain them together to do what we want. So that is exactly the right approach, and that is return-oriented programming. You chain gadgets, and I'll go into what gadgets are, to create something that carries out the attack that you want to carry out. I'll add one more caveat. We're not restricted to jumping into the beginning of functions. Everyone knows that, right? Raise your hand if you understand that you can jump to any instruction when you control the return address. There's one more thing. Nothing forces you to jump to the beginning of an instruction. What? Check it out. So here's the disassembly. We have an instruction here, move RSP, RBP RSP. This instruction is 3 bytes long. It starts at 0x38. The next one starts at 0x3b. We can disassemble just that instruction, and we can get the bytes of it, of course. These are the bytes that make move RBP RSP. We can also say, what about if we disassemble partway through? Suddenly we have move EBP ESP. What if we disassemble 1 byte afterwards? That'll crash. The point is, there are a lot of different offsetted instructions, that we can use to get even more functionality into these little pieces of code followed by a ret. These are called ROP gadgets. ROP gadgets, we're in a demo time, so we'll go back to the demo. ROP gadgets conceptualize these little snippets of code followed by a return that you can chain together to take this bunch of simple, weird instructions that weren't maybe even meant to be executed, maybe aren't even real instructions, but you're jumping to the middle of an instruction and it starts interpreting it as instructions. And you construct it to perform some controllable action. The kind of proof by induction is, at step 0, you overflow the stack. So you control the return address of whatever function you're in. Step n, you jump into some address from the by controlling the return address on the stack, and you trigger, for example, the following gadget. Pop RDI ret. I don't remember which binary I pulled that out of, but these are very common. And then step n plus 1, when the gadget returns, it'll pop RDI of the stack, which you control, and it'll return to an address defined on the stack, which you control, allowing you to go back to step n, control the return address, and go to a gadget. By crafting these gadgets together, by chaining them, chaining gadgets into a ROP chain, you can perform arbitrary actions. So let's exploit this thing. The base case for this is to manually do this shit, and I've done this before the tooling was really created for ROP gadgets. Nowadays, don't do it by hand, please. I'm begging you. I mean, you can do it if you really hate yourself. Yeah, learning by hand is actually not bad. Exactly. So there are tools. One of these tools is RP++. It is present in CTF tools. RP++ takes a file, so we're currently trying to exploit Vuln 3. And it takes a maximum length, maximum number of instructions. So why might you want to limit the number of instructions in your ROP gadget?
Sometimes you have ones that you don't care about.
Sometimes you have ones that you don't care about, but what's worse, sometimes you have ones that, so let's make this 10. You have ones that might segfault. So this one does a bunch of memory accesses. If you don't control REX when this hits, your program might, or if REX doesn't point to writable memory, your program might crash. Let's limit it to 4 for now. So how many ROP gadgets are in this tiny program? 118. Let's make them unique, because you can see there's a ton of rets. It found every ret. Cool. So now we're talking.
Is this just a linear brute force scan of all valid instructions?
This, yes. So the way RP++ works, it scans through them. It disassembles it at every point, and it sees, is one of these instructions a ret? And if yes, that's a gadget.
How does this compare with ROPGAN and phone tools that ROP?
So ROP gadget has some additional intelligence, but it tends to fail more in my experience.
What do you mean?
So ROP gadget has like it'll have something to try to automatically chain these things.
That's phone tools with ROP chain, isn't it?
ROP gadget has it as well. I've never used.
But you
phone
have to
gadget.
turn it on.
You're right.
You have to turn it on.
Yeah, you have to
By
turn it
default,
on.
it just does this.
There's a lot of these types of tools. RP++, ROP gadget, AngROP. Everyone has their favorite. RP++ is a nice, simple base case, easy to use, easy to grep. That's the other thing. Not everyone outputs it on a nice line. Since we have it on a nice line, we can do stuff like grep. We're now talking about setting REX. This is the gadgets we have that mention REX. Unfortunately, it is actually pretty rare to have control over REX. For whatever reason, that is not a very common gadget. So we might be screwed in terms of REX, but not screwed in terms of solving it, hopefully.
Can you give it a desired instruction and have it go and find that instead?
You grab.
Yeah.
Just grab.
Yeah.
Just grab.
But you can with ROP.
You can do a lot, but yeah, grepping, I mean, you can do regular expression grep. You say, I want to have a move, REX, anything.
Yeah.
We don't have that. Do we have REX anything? Of course we do. But unfortunately, we don't have a move. Do we have a pop? REX, we do not. So, we basically don't have control over REX. And no. So, what do we see here before we move on to trying to get control of RX? We see that at this address, there is a return, right? So let's verify that. So here we have a return because RP++ told us we had a return. It's there. Here we have a gadget that lets us pop RSI, pop R15, and ret. Let's see it. We do.
I was going to say, we don't actually need RAX, do we? We really just need RSI.
I mean, which is this called?
So
RDI.
here is what we're dealing with. If we have RAX, we can jump to that, and it will protect a controlled address. Does anyone disagree with that statement? Does anyone not emphatically agree, as in understand that statement? Okay, let's look at this. Let's break here. Continue. So now we're here at this point where we're about to call mprotect. REX right now is 0, right? So let's pretend that we were able to control REX. Let's set REX to 414141, okay? So REX now is 414141. If we step, REX is now a page-aligned address. Okay? If we step, now we're about to call mprotect with that address that was an REX with the second argument of OS1000, the size of a page, third argument of 7, saying execute, read, and write. Cool. So if you can control REX and jump there, we're done. We'll set our shellcode to executable. Unfortunately, it doesn't look like we can do it. REX doesn't have control. So what's the backup plan? If we jump here after controlling RDI and RSI and RDX, if we control all the arguments and just jump to the call to mprotect, we can do it, right? So, does everyone see why? Because RDI, RSI, and RDX are these arguments. That is what adder, len, and prot is to the syscall, or to this function call. So if you can control them and we jump to the call to the function call, then we are set to go. So, can we control RDI? Absolutely. That's a very nice one. It'll take RDI from the stack and then return to the next thing on the stack, which we control. We control RSI. Yes. Right here again. It'll also pop R15, but who cares? Can we do RDX? This one might be tough.
Oh, you're popping R15. That one, oh, no, but that's a call. Oh, move RDX.
Where do you see? Yeah, move RDX R15. So this is our only hope.
What is it called?
So you can control RDX.
It calls a pointer on the stack defined by R12 and RBX.
But we don't need it. We already know we're a literal. RDX is set to a literal.
Yes. So Eric is saying, what if we just jump here? This will set RDX, and then it'll call mprotect. The problem is, it'll reset RDI to RAX. So, can we control R12 and RBX?
Instead of RDX, why not EDX?
It's the same gadget.
What about the DX? Because you only need 7, so you can just keep going until it.
Is it DL?
Might be screwed, guys. So,
Well, wait, how does mprotect work? What happens if you send it in a huge number that happens to have 7 in it?
Let's find out.
What about an OR? Are you some kind of ALU operation?
We just have the move. We have a memory dereference on RDX. We have a move. We have an out, which will segfault for us, so that's a privileged instruction. And we have a memory dereference. Hold on. But we control R12 and we don't control RBX, actually. Bad news. That one seems to be not good.
Well, I mean, we have what about LEA or ASH? So
I just grabbed for DX and we don't have any of it.
If you go to plan 3, you either actually do the sysqual for mprotect, or you can just sysqual for SH.
So are we screwed? What do you think? Why aren't we screwed? We still have libc. So we know, let's do this set arch again. Oh, well, it's here, right? Well, ASLR is off, so we know where the libraries are. Right? Oops, I forgot to set off. So, we're working without ASLR right now. We know where the libraries are. We know that libc is right here. And libc is a ton of code. Our program has 113 gadgets in it. How many gadgets do you think libc has? So here's our libc. We look for all 4-length gadgets that are unique. $41,765. Let's look for just 2-length ones. And let's grab our DX. And let's grab for move. Oh, look what we got. We got to move RAX, RDX. Oh, actually, wait. We just needed to move to control RAX, right?
Oh, yeah. Yeah.
One found. Well, 18 of them, but the one that it gives us is that this offset into libc. But this is inside libc, some random code that is present there that we will jump to have it set RAX for us, return, and give us control back. All right, so let's do it. All we need is RAX. So check it out. So what are we going to do? Where we have the return, we're going to return here, but we need the libc address. The libc address, because we turned off ASLR, is here. You can see it from LDD. Realistically, if we had ASLR on, we would need a leak. Do you remember how you got the leak for the stack? The program printed it to you. Sometimes that works. But it's rarely Christmas. But right now, we have basically this offset into libc. So we move there twice because, well, let's do this. Plus A times 8. This overrides the saved return address. This runs the pop RAX gadget in libc. Does everyone understand why? Then what? Then that'll return. Let's just put a bunch of B's and see what happens. So we're running. We're waiting, actually. Let's do GDB. Boom. Boom. Okay. Let's continue here. All right. So we're step. We're back in main. We're about to return. Where are we returning to? An address in libc. We step. Pop RAX. What are we popping? For some reason, we're popping. Oh shit! I did ×2. Sorry, guys. My bad. Let's restart this. Ah, okay. No, I didn't do ×2. It's the one guy. Hold on, let's see what the stack was at the return. So, I'm sorry? Let's see. So, shell attach 12777. Boom. Fuck. Next instruction. Next instruction. Leave. If it's pwn debug being a fuck. Oh shit! Sorry guys. I'm running on an average of like 4 hours of sleep last week. Okay. This is not our stack. This is our call stack, which is garbage. This is our stack. So this is where our SP is pointing right now. We're about to return to this. Do next instruction. Now our shell, our stack is pointing to this 424242. We're about to pop it off and return. Next instruction. We're about to return to this garbage. What is RAX? Four two four two four two. We control RAX. Amazing. So next, we want to achieve actual control of RAX. Instead of B, we wanted to pop off the address of our stack page, and we can grab it from here. It's this one. So that's roughly where the shellcode is. It'll align it properly when it runs. Wait, is it? We want the address of our shellcode when we were calling read. So where is read? Scroll up. Where were we in read? That's main. Whatever, this will work. This is roughly our shellcode. Yeah, here's our 0000. Is it? Whatever, let's pass in this. Hopefully. So this is what will get popped into RAX from the stack. And then we want to return from the gadget into the mprotect, right? So let's look at protector. We want to return right here. Amazing. We hit that. Let's see what happens. So, pgrep. God damn it. Okay, well, but pwn tools doesn't always close things properly, like it's supposed to. But we know it's that one because we noticed the other one. So attach to it again. Go. We start stepping through. So we're in read, boom, 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 boom. Here's our pop RAX. And you can see it's looking ahead on the stack. Pop RAX, and when it returns, it knows it's going to go to the protector, as it should. So we keep going. We now control RAX, and we have it set to the address of what is presumably our shellcode. Here's a 48. I think that's an H. So let's look at disassemble it. Hey, look familiar? All right. RAX is pointing at our shellcode. We step. Here's RAX. Here's the page address. Next, next, next. Boom. Let's see what mprotect returned. 0. It succeeded. So now, if we go, I forgot which process this is. This guy, if we go to info proc map, we can see that our stack, are you serious? It doesn't, VM map is better. There. You can see that our stack has become executable right there. Yes. Huh?
Right where it matters.
Right where it matters. Targeted executable protection. Cool. So now, okay, so where are we right now? We're NOP, leave, and then we receive a SIG bus. Why did we receive a SIG bus? Because we fucked up our base pointer, and it wants our base pointer to be valid because it is trying to pop something off of it. Doesn't matter. We know where that was. It's these A's. Does everyone understand why we need the base pointer to be valid? Because it restores the stack to that. So let's give it something valid. Let's point it at our stack because it's what?
Why is it a SIG bus instead of SIG ball?
I have no idea. Accept the mystery. So instead of A's, we write an actual writable address. Run it again. Here's our new thing. We attach to that. Go all the way through. Boom, boom, boom. Here's our gadget. Pop REX. Here's the return. Now we're in protector. And protect runs. REX is 0. And protect return success. We go. Protector. The leave survived. And now the ret is about to return to something.
That's going to fail, yeah. That's like an
What is that? That is our shellcode.
Yeah, that's a shellcode.
Why is it returning to our shellcode? Because we controlled the it restores. This got restored into the base pointer, and now that is where it expects the return address to be when it returns. That's a very confusing thing. We went down the rabbit hole a little more than expected. So let's just point this at.
Point it at where it is in the debug right before that.
Yes, we'll point it at where it is in the debug right before the leave. And we can scroll up and check. There, right before the leave, it is pointing to something weird still.
No, it's that one.
Huh?
That. It's that 7FF D400.
Yeah.
That should do it, right?
So this is where it'll leave to. Shell. Attach. Boom. Let's go. All right. Ret. Here's our gadget. Ret. Here we are. Calling mprotect. Here's our leave. And we're back in main. That's interesting. So we're back in main, which we didn't want to be. Okay. Let's, I think our stack already got fucked up. Let's redo this. I know what's going on. We could do a new gadget, but let's not. Okay. So where is our? Here's our shellcode at 3E0. Next. Ret. Pop. Ah, when main leaves. When main leaves, bad things happen. We're not overriding enough. Main cleans up the stack completely. So let's override some more. So when in doubt, send more data. We send 128 Bs. Attached to this. Exactly. Okay, now you see all those Bs? Those Bs are very calming. They're a calming influence. Okay, main returns. Pop. Ret. Boom, 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 boom. Calls and protect. Leave. Right, the B's. Ret. It's about to ret to a B. Huh? Perfect. So, we can use cyclic to find out where. So we put the pwn.cyclic, and you remember we were using that with PETA. But if we're not going to do that, we're just going to jump to our shellcode here. So if you write enough of our shellcode address, we'll be golden. Where's our shellcode? It's right here. We run it.
You only did it once.
Thank you. Times 8. Okay. We do the shell again. Okay. We attach to this poor sap. Continue. Boom, 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 boom. Gadget runs. Boom, boom. Next gadget, in some sense, this is an mprotect gadget. Not leave. We're about to return.
Come on, shellcode.
Woo! All right. Now let's.
So easy.
So easy. All right, let's remove this.
We've done level 3 now, right?
Boom!
We've done level 3 without ASR.
All right. So you can see the difficulty just ramped up a little bit. So I'm glad actually I decided to give you guys the extra week for the shellcoding because we covered maybe 2/3 of what we were supposed to do. Believe it or not, you're going to cover how to do ROP if you don't have access to the binary. Yeah. If you don't have access, you just have a remote. Okay, so obviously the homework right now is still the shell coding. I'll push a couple extra levels, but there's enough there already to get the full 110, as people, of course, have. I'll push a couple extra ones, and I'll push a couple of kind of simpler ROP ones if you want to start exploring that concept. So basically, you have essentially 2 overlapping homeworks that you can realize.
Yeah, exactly. I know there's also one earlier. Yeah, I've been going through the instruction. Has anyone done anything? I wrote stuff. I told them what to do.
Are those route problems going to be actual homework problems, or are they practice problems?
They will.
As in, will I be able to copy paste my scripts if I start early, or are they just to help people get better route?